Hello, this is an in-depth documentation of my physics project, which was the double pendulum simulation. But before I get started, I'd like to dive into kind of what happened to my original project, and why I changed it to the double pendulum project. And the reason for that was that I had a lot of it done, but unfortunately I couldn't get some of the crucial elements of the physics to work. Although I did get some basic animations down, as well as some basic input. Um, Unfortunately, I couldn't figure out how to code in conservation of momentum. So, when particles collide, since they're different masses, proton, electron, there should be some sort of momentum transfer. And additionally, once the particles collide, they remain static, even though they should be influenced by other particles. And I just felt that these flaws didn't really make it a great physics project because it was missing most of the physics in my opinion. So I decided to do something that I'm glad I did later because other people presented on the exact same thing that I did here. But the double pendulum problem, which I believe I learned so much more from, and also I just found more fascinating. So that is the reasoning for why I decided to change my project focus onto something completely different. So this is my new project, which is a simulation of the double pendulum problem from chaos theory. Um, and I wrote this simulation in Python because I thought that would be the easiest language to do it in. Uh, and I also wanted to learn more about some of the animation and math intensive libraries that Python had to offer. And in this case, I used matplotlib for the graphics, scipy, sympy, and numpy for the physics. Before I do an in-depth analysis of the code, I'd like to just kind of run through the simulation so that you have a better idea of kind of what I reference in the code and kind of what the overall simulation looks like. So this is just a single double pendulum being displayed here. And up on the right hand corner, I have the percent kinetic and percent potential energy uh, at each instance being displayed, and the total energy of the system being displayed. And this pendulum is set to have 1 kilogram masses, and the length is 1 meter each, 1 meter long each. Um, and actually, this energy labeling here came in really important when I was debugging this program, because, you know, if I did the physics wrong, you would see that the total energy would change, which is, of course, violates the laws of physics. So that helped me isolate some errors that I made in my programming and help solve them. So that was kind of cool. But, anyways, this is the basics of the simulation. Let's just dive into the coding. So I want to start off by talking about double pendulum.py, as I think understanding this will help me better explain the stuff that goes on in main.py. So first things first, we have a double pendulum class, um, and its instantiator, which I passed in some initial conditions. I state is an array with this information. Um, of course, I pass down the lengths, the masses, and I'll explain this optimize parameter later. But anyways, I store these parameters and also create some new ones like origin and store them in internal data fields that I've created for this class. The next function I want to talk about is called getPosition, and all it does is returns the list of x and y coordinates for the location of the masses of the double pendulum. And the way I've calculated that is using the physics equations that I derived in the theoretical analysis. Next, I want to talk about three different but related functions, which is calculate energy, get potential energy, and get kinetic energy. Calculate energy is pretty simple. It just returns these methods summed up. Get potential is also pretty simple. All it does is just dot in the y vector, y position vector, which is the corresponds to the height in the mgh equation, and dots it with a weight vector, an mg vector, so to speak, and it returns that. Get kinetic is also very similar, although instead of dotting a weight vector with the position y vector, it dots the velocity squared vector with a 1/2 m vector to get 1/2 mv squared, and it returns that. This next function is probably the most important function because it handles kind of all the physics that I derive from the Lagrangian. You can see I just set some parameters here, but this is the main part of the code, and I've split it up into two kind of chunks of math, here and here. And this is where the optimized variable comes in handy. So if I want to optimize a simulation, I run this bit of code, which is just kind of the omega 1 and omega 2 prime, but pre-solved. So it's just a simple plug and chug situation. And then this here is the unoptimized version, and this actually directly corresponds to how I solve the equations of motion using the Lagrangian. And instead of just plugging and chugging, it's plugging it in and solving a system of linear differential equations by using a matrix right here. So that is the difference between those two bits of code. Now, before I get into the next function, I'd like to take a brief moment just to talk further about this equation here and where I got that from, as well as how this directly relates to the equations of motion I derived from the Lagrangian. First, let's take a look at this website. This is the website where I got the equations from. You can see that their pendulum they have is more interactive and just much better than mine. But anyways, they solve for their equations of motion using tension, so quite different from my Lagrangian approach. But regardless, they got the same result, which is this set of differential equations they have here. Now let's compare the math that I have here and the equations of motion that I've derived from the Lagrangian. As you can see here, this is the theoretical derivation of the equations of motion from the Lagrangian. Now down here, I have my results. These are two equations I'm going to use, and they correspond directly to the code I've written here. As you can see, this term corresponds to this term, and this term corresponds to this term, and then this term corresponds to this C2 term. And I've done this for both equations, and then I've set these constants as coefficients in a matrix, a 2 by 3 matrix, and solve that matrix in order to get omega 1 prime and omega 2 prime. The last function I'm going to talk about in this file is called step, and this actually runs continuously each frame of the animation. And all this does is just calculates a new state given the current state over a time interval dt, and it solves the differential equation that I've written and get omega prime. And this differential equation solver is from the scipy library, and it uses the fourth order Runge-Kutta algorithm to numerically solve. Now I'd like to talk about my main.py file. First off, we're running the simulation at 30 FPS, and this is just some stuff to help set up the canvas that the simulation will be displayed. And the main function in this file is generate pendulums. Now what generate pendulums does is, given a parameter n, it creates n amount of pendulums and returns them. So what I do here in this loop is just loop from 0 to n and create a new pendulum and add it to an array of pendulum, which is then returned. Now if you notice here, what I've done is to demonstrate how chaotic the double pendulum system actually is. I've created some code here to skew each pendulum a couple billionths of a degree off from each other. And this is the second angle that will actually be skewed in this manner. The last function I'll talk about is animate, and this is what runs each frame of the animation. First, we step through the pendulums, and then we get the position of the pendulum so the canvas knows where to display it. And then additionally, if there's one pendulum, we can display the energies of the system. And then we also display the elapsed time. Now, I'd like to do a quick little demonstration of my simulation. What I've changed here is I just randomized some variables and I've generated 3 pendulums instead of 1. Let's take a look. As you can see, I randomized the lengths the arms of the pendulums, and also the initial state that the pendulums start at. So this is kind of what it looks like. Uh, you can see that I kind of messed around here. I was trying to make a user interface that allows you to change these variables in real time, but I didn't quite get to that point. The final demonstration that I like to do with my simulation is to demonstrate the chaotic nature of the double pendulum system. And to do this, what I've done is I've set each pendulum with the same parameters except for the initial condition, which I've just changed uh, by a billionth of a degree the starting position of the second angle. Now let's see what happens with a system of 10 pendulums. Now, what we can see is that the paths of each pendulum quickly diverge over time, uh, and that kind of indicates the chaotic nature of the system. Even though we started at virtually the same initial conditions, we're off by a very small factor here. Um, you get a completely different result. Anyways, this has been my physics project. I really hope you enjoyed. I certainly learned a lot coding this, as well as just learning the theoretical Lagrangian mechanics behind this motion. But regardless, I really hope you enjoyed watching this video, and I hope you learned something from this presentation.